bloop. We're recording right on time. Actually, you're not. You're 6 minutes late. um. Anyways, let's do question number. You said it 4. Let's do it. Yep. Oh, okay, cool. Because it's the first quadrant, this one sucks. The reason why is because if it said at all, I could have said 0, 0. Like, what's the center of a circle would be the center of the circle. Like, okay. So, yeah, let's do some work on this. I'm going to pull up a blank. Okay. Good. And yeah, I think I'm going to want more paper. Okay, cool. So yeah, what we have is a circle, but only in quadrant 1 at A and at A. Now, if they would have had a number, that would have been nice. But if I do this, you will always have the answer. Everybody's answer is the same on this one. In fact, why don't we just get it wrong 3 times and copy down the answer and put it back in? Did I just say that? So you're not really struggling with this problem. You're struggling with the concept of this problem. Oh, okay, cool.
I actually got it wrong. I didn't write down the answer. So
Oh, we'll go get it wrong again. So if I had to take this shape right here and balance it on my finger and have it like, not fall off my finger, like where would that be? And I'm guessing it's somewhere around right here. For sure, I can tell you one thing. It's going to be at the 45-degree mark, right? Somewhere along that line is going to be where that center of mass is. So at least we have a little bit to go off of here. I just need to know where in there. Okay, so x bar is the double integral of f dA divided by double integral of dA, essentially. Oh, no, it's not f anymore. It's x, right? And then we do the same for y. And I think if I found x, it's going to be the same for y. They're symmetric, right? Again, 45 degrees, x and y are going to be the same. So yeah, let's start finding it. How do I find the quarter area of a circle? About 1/4 of pi r squared, r being a in this particular case, right? We got a quarter circle. What's the area? Boom. Now, that doesn't help us for the top at all. We still have to do math for that. But we're getting there. We're getting there. I feel like I want to use polar form. Would you all be okay with using polar integral stuff? Here, I don't like where that is. Like here, for example, I'm only going to look at the top here, okay? So this is what we're looking at. And I want to do it in polar form. So x, what does x turn into when we go to polar? Oh, whoa, Chad. Whoa. It will be that, yes. Required r. Very good. Now, if I'm doing my r, I'm going from 0 out to what? A. And then my angle is from 0 to? Perfect. There it is. So you're right about this being r squared. So then it'll be r cubed over 3. That I'm going to plug in 0 to a. Plugging in the a, I get a cubed. So you can just toss that out in the front. I'm going a little fast. Cosine goes to a sine. From 0 to pi over 2. Pi over 2 plugs in to make a 1. And that's going to be my numerator. That's my numerator. Oh my goodness. My numerator. This was my denominator. And then I just kind of mush them all together and be happy about it, right? Notice that I got a cubed and then a squared. Wouldn't a lot of those cancel? And then, yes. The 4 is going to come up. So I think my x bar answer would be 4/3. Well, there's a pi down there. I'm going to leave a pi down here and then put an a up here. And then just duplicate it twice because it's x and y should be the same. So 4 parentheses. Okay, hold on. No. Yes. 4a 3 pi. No. 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 No, I'm sorry. Go ahead.
No, you offended me, Chad.
You're just watching me struggle with this stupid problem. Okay, at least I got a separate one finally. Okay, and then between them put a comma, and then a parentheses, and then a parentheses. Oh my goodness, we got it. Okay, I probably should just click. Probably clicking would be better. Now, go ahead. You were going to ask, maybe? I don't know. Because I just shut you down, bro. I'm sorry.
Oh, no. I was going to mention how you can simplify it, but it's fine. You simplified it.
Okay. Cool. Okay. That was okay, though, right? Switch to polar. Any others since I'm here? Remember, you're keeping me from the Jacobians today.
If you want, Chad, we can get all my homework done today if you want.
Yeah, I have a problem with number 6 and number 7, number 8, number 9. Let's do it. 15-2. Well, now y'all are freaking me out. Because if you know what it is by a couple words, yeah. Well, I do have the power to delete it, so let's check it out.
It's not bad. It's just weird.
Oh, we did this one. We did this one, didn't we?
One similar to it, but we didn't do this one.
Okay. So yeah, we're just taking the integration of that thing, right? It's going to be arctangent from negative pi to pi, and it's kind of like a rock and roll kind of situation here. So yeah, I'm not scared of this one. Because x. Oh man, I don't like that. Because x and y are fairly independent of one another, I'm thinking along those lines. So we got like this guy, and then we got this guy. Dx, dy doesn't really matter. Whatever. This one right here, I believe, is just arctangent. So then yeah, I got arctangent. But I think it's 1/5, and then it's x/5. I think that's how that works. From negative infinity to infinity. I know my math is really sloppy looking. You keep laughing it up, bro. It's fine. I mean, technically, it's not wrong to do what I did. It's just kind of meh. Whenever I plug in these guys, I'm going to get this whole thing turning into a pi/2, basically. So then 1/5, I got pi/2 minus a negative pi/2 times this stuff, dy, I guess. So that's just a pi. So I've got pi/5 in the front, and then we simply just repeat what we had for this one. So that would be a 2. So then I got 1/2 arctan of y/2. Same thing. So that would be a pi. This ends up being a pi essentially, right? Because the way I plug them both in. And so then I got pi squared over 10, I believe. Because there's 2 pi's in the top. And then I got 10 in the bottom. You want to know the formula for this one? My math lab, why would you do me like this? I'm going to be such a bad teacher in just a second. Look, without going, whoa. Hold on, okay, there we go. 5 and 2 make it 10. I really shouldn't have done that. I hope. I mean, it's not that bad of a problem. I don't know if it's exam worthy, but yeah. Is that okay? We don't need to do limits and all that stuff. This is calculus 3. Is there something else? I don't know if you're thinking, wow, he just makes it look so easy, huh? Well, maybe because I'm not intimidated by it. I see infinities and I'm like, plug it in. So, yeah. Are you intimidated by infinity? Okay. That's funny. Yeah. It's a lot of number. Anything else? We're not doing Jacobians today. I don't think we'll have time, but we can definitely keep going what we're doing.
I can pull up my laptop and start naming some questions if you want. Not actually questions I stuck on. Not quite. Yeah.
Let's go finish up the one we were doing, and if you have a question, then we'll do that then. Because like we did this half. Now I want to actually do it. I did this before class, even before James got here, and I got it wrong 3 times in a row. I'm not kidding you. And there's the answer. We already know what to do, and I still got it wrong so many times. And I know y'all already have this in the notes, but I'm just gonna make sure. This was a 2 pi. This was what? That's a pi over 2.
Yes.
This was a 0,
Correct.
and this was 7 cosine of phi, and this was a 10. Okay. So now I actually just have to do it. That doesn't sound too hard, Chad. I got it wrong 3 times in a row. So, well, kinda, yeah. And y'all are gonna help me a little bit, unless you want to do a you do. Is this a you do? I'll have y'all do the next one. Those eyes, man, they tell me a story. You can do it? You can do it? Okay.
So I'm over here to say it one more time.
Oh, you know what? We can do that. Did you want to show everyone else how to do it?
I mean, I can try.
Did you? Is it yes or no?
I'm saying we do it like you. That's all I'm saying.
Yeah, do it. Okay. I'm fine with that. Try it out. Hopefully y'all get it right the first time, and then you can say, "Oh, look, I'm smarter than him." Because you are.
I don't know, Chad. That's some dumb questions this semester.
No. I think what makes me look smarter than I am is because I'm utilizing what I have to the max. I'm maxing out my capacity, but it's not a very high capacity. And my wife always says, "You don't have to put yourself down to lift up others." I can't help it. Normally I would be doing it too, but I already did it. So I just want to make sure I can get it right the 4th time. And overall, I think it's an easy problem. Maybe I was just over or under thinking it. It's so hard for me not to distract you right now. that a thinking face?
Yes.
Oh, okay.
I'm trying to figure out if I should do a trig identity or if somebody else was supposed to do.
I know. I went down that road and it was bad. Don't do that. That was the wrong path. It's not that bad. Yeah. 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 If you're doing trig identities and stuff, it is definitely not the right path. Definitely not.
So if that's the wrong path, I assume you sub.
Oh, yeah. There's a lot of that. I know. You know, my problem is that I did not distribute. That was my big problem. You would think, wow, that's simple. You want me to do it? If y'all hit brick walls, I'm okay because we can do this together. Are you ready? You want me to do it? Shrug. Okay, I'll wait until y'all. Oh, you're good? You're ready? Okay. Oh, you said oh.
I think I figured it out.
You figured out what you did wrong.
Know what I need to do.
Mm.
Then I'll let you know when I get it wrong.
In the meantime, I think I do need to actually get going a little bit here. But the main point is like, what brick walls did we hit along the way? Here we go. So R is going to be the first integration thing. So what do we get for my, not R, I say R, my row. What do I get for that instead now? When I integrate this little guy? Yes. 1/3 row cubed. And then I still have this thing. Whoa. And I'm plugging in both of those things. D phi, d theta. Oh, that's a cube. That's a cube, not a square. And then I'm going to plug these guys in to get 10 cubed minus 7 cubed cosine phi cubed, cosine cubed phi or whatever, sine phi d theta. And at this point, I did not get it wrong yet. Because when I did it wrong, one of the times, I just forgot about this entirely. And then I had to integrate cosine cubed, which was terrible. So, no cosine cubed in our futures, because I'm going to distribute this instead. So I've got 1,000 sine phi, and I think that's 343 cosine cubed sine d phi d theta. So already, I'm avoiding my mistake. Did y'all do what I did so far? Yeah, it's these little things that get us. I know. So integrating this guy is actually not too bad. Sine, when I integrate it, will go to a and what I'm going to do here is the u sub. So I'm saying that u is equal to my cosine. So what would be my derivative of cosine is negative sine, very good, because we have a negative sign. So what actually happens is it ends up being a positive there. Two negatives make a positive kind of thing. And then I integrate 1/3, which will go to a 4/4. So then I've got cosine to the 4 phi. Back to the blue. From 0 to pi over 2. Let's pause on that one. I skipped a step or so, but in the end, I'm trying to make it more efficient in the end. without having to do a whole ton of stuff. And already, again, I avoided one of my bigger mistakes. Another time I got it wrong, I had a sine right here instead of a cosine. I mean, it's just these little things where if you're going through it, you're like, oops, forgot that. That's pi over 2, my bad. Okay. When I'm plugging in the pi over 2, cosine goes to a... No. I'm plugging this in. So what at 90 degrees, what's my x value is? And then I plug it in right here, I get a 1. So then I basically just say this dude here. Plugging in the 0, cosine of 0 is 1. So I get a 1000 there. And then cosine of 0. Oh, I did it again. Did you see it? Look, right here. I plugged in for cosine, I got a 0. I plug in for cosine, I get a 1? Well, to the 4th, but yeah. Oh. Well, I'm only doing this part, plugging it in. So that 4th comes later. Therefore, I would actually get a 0, and then 4th power is still a 0. Man, see, I still messed it up. It's okay. I knew something was wrong. Plugging in the 0 here, we get a 1. Plugging in the 0, we get a 1. Okay. Whew. Because this is, okay, how about this? How many thetas do we have in here? Nothing, right? So when I integrate, I add a theta, 0 to 2 pi. So I just basically put a 2 pi in the front. And that makes it a lot easier. Oof. Calculator time. This is a negative. Oh, you mean like from earlier? Oh, we're subtracting those. You can't. You're right. You know, this is why I get it wrong a bazillion freaking times. Okay, look, then we're going to do this so I don't feel so stupid. Thank you. Yeah. Like, hold on. Let me get this out the way here. Okay. And shrimp. Okay. I just can't help getting it wrong every time. So 2 divided by 3, and I got a 1000 minus 343 over 4. And then you just add a pi onto it, and we're done. And that is the answer. Because I've done this now 5 times and still gotten it wrong, even on the last one. And you know, they're simple things. It's simple things. You switch to sine. I forgot the 4 power. You know, I plugged in a thing and it should have been a 0 instead of a 1. And it's not a complex problem. I think it's just so, and there's not a ton of moving parts. It's just Monday, maybe? Let's just call it Monday. Okay. Anyways, flash the answer, and there we go. Mine looks so pretty, but, well, like you can see, I had messed up my plus sign, which I had done wrong the first time anyways. I mean, I do this all the time. Okay, but are y'all overall okay with just integration, I guess? Cosine integration goes to a sine. Sine goes to a negative cosine. Blah, blah, blah. Okay, moving on. Any questions, though? Okay, good. The other ones are different. So I did these, and I actually got them right. I think maybe the first time. So, but it took me forever to draw these things. So it says we have the cylinder, and then it's cut by these cones. So first off, what does it mean to have a cylinder like that? It's, well, here's a cylinder, but because there's 2 radiuses, it's kind of like there's like a thing in the middle. A bead? Would it kind of like be a bead or like a not a washer, but more like a spacer. A tube. It's a tube. Okay, so we got a tube, and then this tube is going to be cut by the cones. Now, I want to say that this the plus and minus is very important to this problem. Couldn't I do something to make this a little easier? What would you actually call this guy? Help me out.
Wouldn't that be a circle?
Yeah. In fact,
Take out the 3,
yes.
and then you would still be left with the cosine x squared plus y squared, which just equals
My, haven't I seen that before?
r.
Yes, exactly. Now, and over here, I can say that this is between these two guys. R squared is between these two guys. So then my R would be between these two guys. So I'm already kind of getting some limits of integration going. You can see that we're going to go to like polar / cylindrical mode because it's cylinder anyways. So we're already getting pretty close. But what do these cones even look like? Like I know what a cylinder looks like, but what does a cone here look like? Well, that is not a cone. That was not a cone. That was a scribble. A cone looks like this, of course. But because there's plus and minus, it looks kind of like that. Our problem here is that we need to take that cylinder and cut it along a cone. Okay? And so let me show you what it's going to be. I'm going to use the cylinder in orange. I think I want it a little bit more than that. Give me a second here. I'm going to do this, and this is my cylinder. What they're wanting is not the inside of it, but the outside of it. And then like on the inside, we have this little thing going on here. So in the end, and I'm going to try really hard to make this look right. On the outside, the cylinder looks fine because like the cone cut it right here and right here. The cone would be like coming out of it because the center of the cone is right there. But what happens is that the inside of it, that little tube part, it was also cut by that cone. You can see that it like that inside part doesn't stay the whole time. And so my actual shape, it more looks like this. It's a tube, but then it's been kind of like drilled out by a cone on both sides. So it has some of that inner tube, but not as much. Okay. So yeah, a cylinder, big cylinder, and then there's like a little cylinder inside, and then you're just connecting them like this. That's basically what this shape would look like now. Okay. Find the volume. Is this a you do? No, I'm playing. Like it's a little weird. So if you want to go to Desmos graphing, are y'all okay with cheating on that? In that? Oh, you are.
I mean, like homework trying to understand the problems, I think it's perfectly fine.
Yes. So there's my cone, and then I've got 4. No, it's not r equals 4, it's r squared equals 4. But see how this is, it's just a circle. It's not cool, you know what I mean? It's not really showing me what's going on there. Oh. Thanks. Okay. Because we're looking at the inside of it in a way. Whoa. Okay. There. Do you see how right here the cone is cutting into it, right? But then if I do this, the cone is now cutting into the blue a little bit. And here the cone will cut into that green. Okay. I don't know if that's helpful or not. I think that this is not as helpful. So what do we got? We got a cylinder and we got a little cylinder, and you connect them like that. Cylinder, cylindrical. So triple integral r dz dr d theta. That's our basic setup. Even if you don't have a perfect picture, we still have our limits. And our limits, we're simply going to plug them in. So let me use a different color to emphasize here. This is a z equals, and this is a z equals. This is an r equals, and this is an r equals. And then we got thetas at the end. Not a big deal there. I think that's an easy one. So do we have a z equals somewhere? There you go. So what would I put down here? And? Beautiful. That was easy. Do we have an r equals something around here? Two square root of 5. And then what would be my thetas? Thanks, James. Are the rest of y'all okay with some of these limits? Like, even if we don't know what the picture is, we can at least like plug some numbers in? Is that a yes or a no? Yes? Halfway. Yes or no? Okay. Because like we can solve for z, we can solve for r, and then I don't even know what the pictures are, but at least I can do plus and minus, right? That's kind of like my bigger picture there. Here's the thing. I don't want to waste a ton of time to see if this will work or not. So let's get it wrong 3 times. Bloop. And that's the answer. Don't look. So 4 pi, notice that my MATLAB did not have it simplified. Ooh, bad MyMathLab. I want to show you a technique because I was using this morning to, I guess see if I can get it right from Desmos. So what I'm going to do is pull up Desmos graphing, and I'm going to do some integration. I want to get that integral to be the same. So 0 to 2 pi. We got 2 to square root of 5. And I know that we're not always supposed to do this. I get that. But you don't want to waste a ton of time on your homework. So this is what we get for this guy. Okay. Now let's do the decimal equivalent of the answer that I got from MyMathLab. Are they the same? See? So what we did is good. Our integral is perfect. Now, again, I have to do this over again. If you ever see the answer on MyMathLab, you got to do it over again to get the right answer eventually, right? So when you get a new problem, or it might be the same numbers, you never know. You just repeat the same process. Very, very simple process, right? And then now we have to integrate. I'm just kind of verifying, was I down the right road? Did I actually set it up okay? Now, here's one other thing that I want to do that I did that y'all didn't. Notice I had a 2 in the front. You see that? Because I know it's all symmetrical. What I could do is say 0 and put a 2 right there. I'm basically saying like from here upward and then double it. So take half of it and double. You can't do that with the other guys, but you can do it with this one at least. Cool. So let's integrate this thing. We don't have a z, so we put a z in, and then you plug it in, and yay, it's no big deal. It's 3r squared now, dr d theta, because there was an r, and then basically this r here makes an r squared. When I integrate the r squared, what do I get there? Beautiful, beautiful. I'm mushing the 3 and the 6 together to make a 2 in the front again. So I got square root of 5 cubed minus 2 cubed. I don't have any thetas, so what do I do there? 2 pi slide, man. Whoever taught you that was really cool. Oh, that was me. And you can see we got the answer now. That's a 4, and everything else is the same. So, yeah. Cool. Yeah, 2 pi slide. I got it from Lyles, so yeah. Yeah, he's He's way better than me. Talking about intelligence, that man is far more intelligent. So, and now he's a dean. Okay. I mean, he might say so, but I mean, he's, he's important. We need him. He does good things for us. Okay. Cool. Are y'all okay with my silly little cheater trick? To at least kind of see, are we down the right road? I don't want to spend 30 minutes on this thing, you know what I mean? And if it does work, then I can go back, put in my own new numbers, walk away, right? So let's do this again with this one. Same style, and then like we're done with that section, right? So this is also not too bad. I just had to kind of think about what it meant. So we got a cylinder, and it's solid, which is very happy. That means like it's totally filled in. We don't have like a pipe thing on the inside anymore. So we got a cylinder. Sweet. And then we have a sphere. It says they want the cylinder, but it's cut by the sphere. Cut by the sphere, okay? As in when I put the sphere on there, yeah, it's going to cut into the cylinder at some locations. Now, we know that the cylinder is not going to change its radius, so it's somewhere up here. There's like a little cut, and then there's right here. Okay. So if I were to cut it, I mean, it looks like a cylinder again, right? But not quite, because the sphere made this kind of like bubble dome thing up here. Okay, so I'm not going to do the dashes because it's actually a solid. So there's actually a dome up here and a dome down here from that sphere. If you had taken that sphere and kept going, you could see the sphere now, right? So it ends up looking like, I don't know, what would you call that thing? It's like a cylinder with like a dome on the top and bottom. What is this? A pill. It's a pill. Yeah. Find the volume of this pill. That's what we're trying to find. That's pretty cool. I don't know if I'd like that kind of pill, but okay. Normally they don't have that shape, but it's close enough, right? It's a pill. Good? Okay. Always, or okay, I'm sorry. Never share medication. My little thing. Public service announcements. Anyways. So we're looking for the volume of the pill. Because it's a sphere, I say, oh, spherical. Oh, really? That's what you think? Oh, but it also said cylinder. So which one would you rather have? Which one would you rather have? Cylindrical or spherical? Cylindrical, heck yeah. To heck if I'm doing rho squared sine phi, blah, 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 right? That would just be crazy. Cylindrical. So R, dz, dr, d theta. We're much more familiar with cylindrical. We're comfortable with it. It's easier. Even if sometimes it's not perfect, it is going to be easier in the end. So I'm looking for, again, this is a z equals. This will be an r equals, and then I got my theta, which you can already guess what theta is going to be, right? Yeah, that's an easy one. So yeah, we can definitely say 0 to 2 pi. I'm happy with that. That's no problem. All right. For a cylinder, do we have an r here? Like, can I rewrite this with r in mind? What would that be right here? What would this be? R squared, very good. I got this one wrong because I put it in r. It's not r. It's r squared. So therefore my r really is 5. Good. And because we're doing polar, you're going from 0 out to 5. Okay, so like basically 0 to 5. Those are good numbers there. That's my cylinder. Okay, awesome. So now we got to do the z. Okay, sorry, this is just in the way. Okay, now I got to do the z. The only thing that has z is this dude over here. Wait. What is this guy again right here? Oh. How do I get z by itself? Yeah. Move it over in square root. Very good. So move this guy over. Square root. And I got this one wrong earlier because I didn't square root. I mean, those silly little things like that. Now, I knew I was wrong before I did the integral because I had gone to Desmos graphing. I tested it out. I was like, oh, yeah, I'm getting it right. Go ahead. And it is definitely plus and minus because we have the dome on the bottom and the dome on the top kind of thing, right? It's the wrong picture. But yeah, dome on the bottom, dome on the top. I don't want to put negative and positive here because I'm too lazy. So I'm going to do a 2 and then do 0 to the square root. And it makes it a lot faster because I don't have to do 2 different square roots, which scare me. So now I'm doubling it. Again, I'm saying cut it in half. I had my cylinder, and then each one had a dome, and I say cut it in half, only the top, but then times 2. Do you mind if I get a cheating method again? Bless you. So first off, we have to get it wrong. We'll come back to that. We have to get it wrong. Was that the one this is the one we're on. Let me write down the answer. So 4/3 pi 216 minus 11 square root 11. That's what they have. Okay, so 2 times the integral 0 to 2 pi. Integral 0 to 5. 0 to the square root of 36 minus r squared. R dz dr d theta. And then I'm going to compare with what they got. So 4/3 pi 216 minus 11 square root 11. Did we get the same answer? Yes. Because we got the same answer, now I know that when I do my integration, my integral, my basic, my start is correct. I can see that y'all are already doing it. That's good. Correct, though? We're good? So now I can actually do the math. I have my z, but I don't have any z's. So then I just toss these both down in there. So I got r times the square root of 36 minus r squared. The 0, of course, goes away. And what do I do at this point? U sub. Yep. Now I did not do U sub. If you go and look at my silly little answer, I just went whoop. Because I did like 5 steps in my brain. And like for once I actually didn't get it wrong. So that was kind of nice. So r square root of u, and then I have a du over negative 2r. The r's cancel, the 2's cancel. I actually get a negative integral of u to the 1/2 du d theta. When I integrate u to the 1/2, I get very good. And I'll just go ahead and re-plug in my u from 0 to 5 d theta. Now, I was stuck. I was stuck at this point. I need a positive answer. And if I plug in the 5, don't I get a negative or something like that? The answer is no, Chad. 36 minus 25 is a positive number. Yeah. Hey, go figure. That's what they got. Like it's funny how like where I get stuck. I get stuck right here. That's where I got stuck. I was sitting there like just staring at it like, what? When I plug in a 0, I get 6 cubed, which I hope is that 216. Two pi slide. So now it's going to be a 4 pi in the top. And you can see that they're flipped. My signs are flipped, but then again, I have a negative in the front, so we're good. And there we have it. We did it. Darn, we still have 5 minutes, so I have to do Jacobians. Yes, it does. It should be. And one time I did one of the other problems. I got a negative. Oh, but it was correct. Just change it to a positive. You'll be fine. You'll be seeing that a bunch here in chapter 16, because I get things flipped sometimes, and it's just, yeah. Well, not always, but like if it doesn't work, try the positive, and you'll probably be fine. Yeah. Okay. Cool. Maybe I shouldn't use that word. Complete. Complete. Any questions? Okay. I do have 5 minutes. I do want to spend it with you guys because y'all came late, except for James. So let's go. I'm not going to go too much further, but I do want to talk about Jacobians and start you off. The first problems they have are really simple. Most of the homework for Jacobians is easy. In fact, you know what I'm going to do before we even get started? I'm going to go to that assignment since I have them up, and I just want to look and tell you, yeah, this is easy, yeah, this is easy, yeah, this is easy, or, ooh, that's kind of hard. There shouldn't be too many in this section. 6. All right, I think you got this, all right? But anyways, this one's not too bad. It's just solving for little dudes. This one's pretty easy. Again, just find the image. That stuff's not hard at all. This one's a bit difficult. That was the one that I got stuck on today. It's just because there's so many flying parts going on. This one's much easier. The way it's structured actually makes it much easier in the end, so I like that one. This one is not too bad. I know that looks a little bit weird, but like, look at what we're doing. That one's weird, but it's easy. That one's super easy. Look at how weird this thing is. Come on, go ahead and integrate. Go on. Like, what are you talking about, Chad? So the point of Jacobians right now, I'm going to tell you, is to make these really crazy integrals easier. Okay, like even this one is insane, but we'll get there when we get there. Okay. So why do we do Jacobians at all? It's to make hard things easy, okay? And I'm not going to say easy as in like, oh yeah, there's a cakewalk, but like the second problem that we will be doing has this like area, this zone area of like this way, and you're having to integrate over this area here, and nothing's horizontal. It's all kind of like this weird trapezoidy thing. Go ahead and integrate using the area of this and variable density, have fun. And you're like, what? I have to do like 3 or 4 different integrals. Or you could do Jacobians. And Jacobians are, a little bit of upfront work, but we could do that. Here, let's redo this formula because this one's nasty. Notice, this is x, this is a DDU of x, so it's x sub u. And then times y sub v minus y sub u times x sub v. There's your better formula. I don't know why they don't put these easy formulas in. They just want to look cool. Hey man, look how cool I am. Yeah, that's way better. That formula's way better, okay? Oh, that's right, but y'all are in linear, so determinants are easy for y'all. No. The main thing, this right here again is just so sloppy. I don't like this. What I would rather say is this is double integral of f times j du dv. So I'm converting a dx dy or dy dx into a du dv, okay? I multiply by the Jacobian and everything's happy. And a lot of times, not every time, but a lot of times the Jacobian is just a number. Like like 5 or 2. Okay, so this would just be a number, and you just integrate, and you're happy. Everything's happy. Okay, that's the goal. We want things happy eventually. Okay. Yeah. Okay, you don't have to see the whole picture, but I just wanted to kind of show you there's an easier formula, and this is really what we're doing. Here we go. And we're not even integrating on this one. It says solve for x, solve for y, find the Jacobian. What's the picture? Overall, this is actually really simple. It just takes a lot of little math, okay? So notice that we have these two equations right here. And what I need to do is say x equals y equals instead. I should be saying to you, all right, you've done this before. Go ahead and do it now, and I'll wait. Basically, yeah. I wouldn't want to call this a matrix problem because it's variables and stuff, but it's similar to matrix stuff or systems of equations. So yeah, let's do this. Let's move this over here. So then I got y is equal to v minus 3x. I think that's an easy one. And then I can solve for x. I'm going to move this over and divide by the 3. So I got x is equal to u plus y all over 3. And I could take this and plug it in. So now I got y is equal to v minus 3 times u plus y all over 3. Cancel the 3's. I got v minus 3u. No. Just y minus u. Don't the 3's cancel entirely? I think so. I thought that there was a 3 in there, though. Give me a second here. 3x. 3 should cancel. Oh. Aha. Am I right? Whenever I distribute this 3 here, I mean, it cancels the 3, I guess you could say. When I distribute the minus sign, I'd still have a y here. Add y to both sides. I know this is so weird, but it is just basic algebra. Divide by the 2. And so then we got v minus u all over 2. Happy times. I can now plug that in over here. and I mean, it's just silly little math. So u over 3. This will be all over 6. So I got v over 6. And then I've got minus u over 6. And these guys combine. So 1/3 minus 1/6 is going to be a 1/6. So I got u plus v all over 6. Let's check the answers. Okay, what's up? Oh no. That's not a 4, that's a u. Oh, that's a u. Yeah, no, that's the problem around here, is that my u's are no good. Was that a minus? Okay. You're right. Those are u's. Here, let's go check the answers. So I got divide by 6, and I got a divide by 2, and then it's the u that's negative. Yep, perfect. Yep, so I got them. And you can see I already did the math. Blah, 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 blah. I mean, this is not hard, but it's just a little weird. Like, I am in calculus 3, and I'm doing this, which there's a lot of room for mistake, right? I mean, there's at any moment you miss a sign, it's all over. But I'm going to ask, and I mean, you can be honest. Is this okay math? It's been a while since college algebra. I get it. But like, you're right. We're moving things over. And one thing I almost forgot was a y on this side and over here. I had to move that over. Like, what the heck do we do with that? You know what I mean? Even now, we're not done. We got to go find the Jacobian. I know it's 2 minutes past. I'm so sorry. we're going to finish this Jacobian in the thing. It's not too bad. So the Jacobian is, again, x sub u, y sub v, and then I got a y sub u, and then an x sub v. So I'm using these same formulas here, and it's already x equals, so it's kind of done. So what's my derivative in terms of u? 1/6. Okay. In terms of v, when I take a derivative, minus, now y in terms of u, and then x in terms of v. Positive, yeah. So then here we got 1/12. Well, two negatives make a positive. It's 1/6, and that's their answer for the Jacobian. Again, most of the time it ends up being a number. If it's not a number, sometimes it's like a small little, like a u, like 1/6 u or something silly. Very tiny, should be easy stuff that we get there. And now, which is the picture? And this one took me a long time, but it's not hard in the end. Notice that they gave us these 3 points. And this is, again, this is x and y. So I need to plug in x and y and get my u and v. So what you actually do is go back to the original ones, and you're going to plug in your x's and y's. Is that what that is? Yeah. So then I have x and y is 0, 0. Plug it in. So my u, when I plug in 0, 0, I get, okay. And when I plug in 0, 0 here, I get, okay. When I plug in, my other point was 1, 3. So my u, when I plug in a 1, 3, okay, a 1 and then a 3, and then the last point was 1, -3. I don't know why I put that line, whatever. When I plug that in, yep. So my points for this region would be 0, 0, 0, 6, and then 6, 0. Which one of these pictures use all 3 of those points? You already saw it, right? You already flashed the answer. So right here, right here, right here, there it is. All the others have a negative. I don't have any negatives for my results. There it is. So what we then do is say double integral of this triangle, which is very, very simple. It would be 0, and then this guy is just a 1 thing. So it would be like negative, give me a second here, negative u plus 6, I believe, 0 to 6 of 1/6 du dv. No, it's a v there, sorry. Negative v plus 6. You don't have to do this. This is not what they're asking for, but that's the idea. Look how easy the integral is now. Pop, 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 get it done, right? So we're going to do that again next time. Cool? Thank you, guys. Thanks for hanging out an extra few minutes.